All right, in this video, I'll go over an example problem here where we use dimensional analysis to help model a system and to make some statements about the real system. So a prototype, or in this case, it'll be an actual structure that's built. So the system here is a monument, a proposed monument. Is being discussed about being built, and in order to shed some light on the full system, we're going to be the plan here is to use a 1/10 scale model, and instead of the monument which will exist in the atmosphere or the air, airflow moving around it, we'll be using a water tunnel. And so the parameter of interest here is the vortex shedding frequency. As we saw in a video in class, that flow around objects tend to shed vortices, and the frequency at which that occurs, so these displayed here by the swirly motions, these vortices, the rate at which they're shed is a measure of the potential damage to nearby structures and trees and people, and overall the measure of turbulence that's generated from inserting this proposed monument into a region with a high velocity winds. And so we'll be using here typical steady winds in this area of 50 kilometers per hour. So typical, what we mean is like typically the typical winds that are high. So maximum wind speeds on a typical summer, out throughout the typical summer, right? Because what's really important here is at the most extreme events, what damage are we going to do? So that's about 31 miles per hour. So here's the system. We have h is the height, and then 2 length scales of our square monument. A bit of an idealization here. This is kind of a boring monument. But if we go to the top-down view, here's our velocity, uniform flow velocity for the wind speed, generating vortices behind. That's where we'll take off with this. Our solution then will start by relating all of the important parameters, and where we have the dependent physical parameter. This is what we want to know about the system, the vortex shedding frequency. So therefore we'll call it the dependent physical parameter, and we'll write it as an arbitrary function, we don't know what, of all of these important parameters. So the 3 geometrical properties, the 3 length scales in the problem, depth, width, and height. The dynamical property here, which is the velocity of the wind, and the fluid properties, the density and the viscosity, where we're talking about air in this case, so these are density and viscosity of air. If we count all these up, we have 7 physical parameters of interest written in the 3 typical reference dimensions, whether that's mass, length, time, or force, length, time. Either way, you'll find there's just 3 here. Therefore, k minus r, we should expect to get 4 pi terms. Okay. The next step is to then choose repeating variables. It's always smart, a good decision to start with a simple first repeating variable. What we mean by that is choose one that is just, if it's possible, just one dimension. Right, so we have 3 length scales here. Choose one of them because it's just length. It's going to make things easy. So we choose the depth to be the repeating variable. Now we can't use w or h for any more repeating variables. We've already used up length. These are just length. They're not going to give us more reference dimensions in our set of repeating variables. So therefore we go to velocity, which is going to introduce time. This is length over time. So now with these 2 we represent length and time completely. We now in our third one need to represent either force or mass, and that comes through. You could choose either density or viscosity for that. And we'll choose viscosity, because that way Reynolds number falls out naturally. So that means that the remaining 4, again we've chosen d, v, and mu, so the remaining 4, which are omega, w, h, and rho, are non-repeating variables, and each of those will be associated with a non-dimensional or a dimensionless pi term. And so you would go go through the process of setting up your system of equations for the exponents on each of the repeating variables, or you can do all 4 of these by inspection. And I'll talk through here why we can do this. First of all, if we look at pi 2 and pi 3, where I'm labeling these pi, the pi terms associated with these 4 non-repeating variables as pi 1, pi 2, pi 3, and pi 4. I'll start with pi 2, which is associated with w, which is just a length, a geometrical property of the system. And inside our set of repeating variables, we have one that is just a length. So we can just quickly tell whenever you have these different length scales in the problem that it's just going to be a ratio of the two length scales. And if you go through the process, you'll find the same thing, through the rigorous process of Buckingham pi theorem. Same with the third pi term. It's just going to be h over d, right? So h is going to be our non-repeating variables. If we set it all up, you would just find that it's just going to be the ratio of h to d. For the fourth one, now if we don't look at the solutions here, but we just have the four that we're interested in here, we're trying to find a dimensionless parameter that relates density, a length scale, a velocity, and a viscosity. We know now that that's just a Reynolds number. That's just going to be a Reynolds number, or that's going to be one way to represent these as a dimensionless parameter. So just from inspection by looking at our common pi terms, we know that that fourth one is going to be a Reynolds number. And also from our common pi terms, the table in the book, whenever we have oscillatory behavior in a flow, we can relate it to the dynamical and geometrical properties of the system this way. It's just omega, which is a 1 over time, a length scale, which is a length. So we have length over time on the top and a length over time on the bottom, where d and v are both repeating variables. Again, this can just be done by looking at the table of common pi terms, and then therefore by inspection, just going right to that. Okay, so I'm not suggesting you do this all the time, but if you can either look, is it really simple? Can I just take my non-repeating parameter here and divide by something in my set of repeating variables to quickly know that it's just going to be one over the other because they have the same dimensionality? Or can I go to my list of common pi terms and pull one out of there that matches completely, where my set of the one non-repeating and my all of my repeating variables is going to produce one of these common pi terms. If you can't do it quickly, I would just then go through the whole process. It's not too difficult. Okay, so the next step then, now that we know our pi terms, is to then have a communication here between our model and our prototype, or a model and the real system. We need to then match all of our pi terms. So there's 4 of them in this case. The first 3, the independent ones. So maybe actually I kind of skipped a step here, but the result of this is then we have pi 1 is some function of pi 2, pi 3, and pi 4. And now this must hold true for both the model and the real system, the full scale system, and then therefore each with the same g, the same form of this g function, and so therefore each pi term must also be matched through model design, requirements. So that's what these are. They're called model design conditions, and that they mean that when you scale down your system or go to your model, these must be matched. So all of the pi terms for the model must match the full-scale version. If we plug that in and just put subscripts on all of our models, we know that this just tells us that when we scale it down to bring it into the water tunnel, we must scale them down similarly, all of our geometries of the system. Scale them down so that if you take the ratio of any two, you get the same as what would be true in the full-scale version. The fourth pi term, what we're really doing here is matching the Reynolds number for the flow in the water tunnel to the Reynolds number for the flow in the full-scale system in air. Okay, so this is what tells us is that when we go to our model, we want to have our model subjected to similar force ratio between inertia and viscous effects as the full-scale version. So this is called a dynamic similarity instead of a geometric similarity up here. If we solve this for the kind of the only part of this that we have unknown. All right, so everything here is known. These are fluid properties where, and not anything not with the subscript is referring to the air in the full-scale system, and anything with the subscript m is referring to the water in the model scale system. So these two are just ratios of those fluid properties, and really we can just plug this, think of this as the density of air to water, the ratio of densities air versus water, and this is the ratio of viscosities water versus air. And then this other one is just the ratio of a length scale in the system. And we know that in the problem statement we said there's a 1/10 scale model. So this is just going to be 10 to 1. Plug all these in using standard conditions. We can see that air is 1,000 times less dense, but 100 times more viscous. So this is going to save us a factor of 10 by going from air to water. We see the factor of 10 from scaling down by a factor of 10, And then when I say a factor of 10 here, it's about an order of 10, where this is perfectly a factor of 10. So, in the grand scheme of things, the scaling down by a factor of 10 is being balanced by using water instead of air for a model. That's what the point I'm trying to make. And then multiply it by the velocity of the wind speed for the full-scale model. Okay, after some conversions to get to meters per second instead of kilometers per hour, the result is that the velocity we need to use in our system, in our model system, such that we can make the same, we're really testing what the full-scale model will be subjected to under the, by matching the Reynolds number similarity, is about 10 meters per second. So this is a doable speed to do in a water tunnel, but kind of fast. So you need a lot of advanced experimental techniques in a setup to do this, but it is doable with today's technology. Okay, so let's say you do that, and you can run this experiment. You take you scale down your monument by a factor of 10 in all dimensions, in all geometrical dimensions. You then subject it to a flow speed in water of about 10 meters per second, and you find, and you can measure that the vortex shedding rate is about 7 hertz. So you get about, in the model, you get about 7 vortices shed per second. All right. Now we can go to prediction, predicting something about that first pi term, that dependent parameter omega. So not the dimensionless parameter that includes our dependent parameter, the omega. We set these two equal to each other and solve for the only unknown in this case, which is the shedding frequency for our full-scale system. Now that we know and have measured in the lab our shedding frequency for our model scale system, plug all these in. Now it's 1 over 10. This 50 kilometers per hour I've converted to 13.9 meters per second. It's 7 hertz that we saw in the lab. That relates to, in the full-scale system, we expect to see a shedding frequency of about 1 hertz. So that means that for this monument, you'll get about 1 vortex shed every second for these high wind speeds, which, if they're large-scale vortices being shed this quickly, that could do some damage, or at least make people walking there uncomfortable and have some effect on the local trees and foliage. But so that's kind of answers the question, but I do want to make 2 comments here. One is that if you actually calculate the Reynolds number, so we set them equal to each other in this step here, but if you actually calculate one or the other, I mean, they had better be equal if you calculate both of them, and plug in that it's about a 20 meter tall, 20 meter tall, and give a, so maybe it's about 1 meter in the D here. The D parameter is about 1 meter for our actual monument. You get a Reynolds number of about 10 to the 6. So that's quite large, and what that means is that the vortex shedding will be turbulent. You'll still get vortex shedding, but it won't look nice, neat vortices. Instead, it'll be turbulent vortices being shed, and that does complicate the system a little bit and maybe makes it where our initial set of the problem isn't as valid as we were hoping, which is kind of this idea of vortices being shed kind of works in the moderate range of Reynolds numbers. The other comment to make here is that we never did check kinematic similarity. We checked geometric similarity by scaling down all length scales of the monument appropriately or similarly. We then checked dynamic similarity by making sure our Reynolds number was the same. But we didn't check kinematic similarity, and this would require kind of making sure that the particles, that the general flow structure doesn't change when you go to your model. So do air particles act the same when it goes around the monument in the full-scale system? Does it act the same as the water particles do when you're in the model scale system? And so they being different fluids, that might be something that you would consider, but it's actually hard to always consider all similitudes at the same time.